So hello everyone, I'm here with Fábio. We work for INESC TEC, which is a research institute in Porto, in Portugal. And I'll be presenting a platform that we developed during the past few years. It's called Predico. It's a platform for collaborative analytics. In particular, for today, I have a use case for collaborative forecasting, okay? So, on collaborative analytics, why did we do this? So the idea is you right now have a lot of distributed data, geographically distributed data, that you can use to improve, for instance, forecasting accuracy. However, we still lack proper economical signals to share this data. If you don't have an incentive to share data, why should you? And also the value of data, so how much someone should pay for your data is also unclear. That's a problem for entities that have data nowadays. And if we talk about forecasting, now what happens nowadays is that companies have either their own in-house models, okay, they build it from scratch, or they delegate this task to an external company. They buy forecasts from an external supplier, which might, since you don't know the building process of those forecasting models, those models might have biases in certain conditions, for instance, and might have errors that you are not aware of and that you cannot anticipate, okay? So the opportunity here is to create a collaborative ecosystem where both data producers and forecasters can interact. And here the idea is to monetize participation. This is a key word, through incentive mechanisms based on the value of shared data. So if your data is valuable to others, you should get something out of it, okay? And now how do we unlock this value? We have basically a central platform with a shared data pool, and then we are building use cases on top of it. One of the use cases is exchanging data by data. So if you don't know the value of your data, you could exchange data for the same value, by another data set, and we find that value for you, okay? Data that is useful for the same use case. The other use case that we are building is collaborative forecasting, and this is the one that I'll talk in this presentation. So the idea here is that you combine multiple owners' data sources, measurements data or forecasts, to improve resilience and accuracy of, for instance, ensemble forecasts. So the final forecasts that reach the entity that wants to purchase better forecasts. You'll see that in a second. So we started this in 2020 as an internal research or a seed project. And then this basically was created on top of existing research from our center also. We grew this into a higher TRL doing some European projects that you can see there. And now we are running an actual proof of concept for the Belgium TSO, so Elia Group. And you can see more details about it there, but you'll see it in this presentation also. So this is what we started with, and this stemmed from the paper that you see there in the left, okay? So the idea here is, if I have measurements data spread around a geographical location, for instance, multiple wind farms in a certain area, if you combine the measurements data of those wind farms, leveraging on that spatial information, you can improve the forecasts of the different wind farms that are there. So if they share information with each other, they can improve forecasts of each other. We have proven that in that paper. And then what happens in this platform is that you have an entity, for instance, one of the wind farms, that is willing to buy these collaborative forecasts. They finance this platform, this market, and then you have the suppliers that, if the data is useful to improve the forecasts of the one that is purchasing, they will get something out of it, based on the value of the data. And here we used Shapley values. We have a regression model in the middle, and we use then Shapley values to assess the value of this data for very short-term forecasting. And based on the Shapley values, we distribute the revenue, the payment from the entity purchasing forecasts. Then what happened was that Elia saw this, specifically Herman Carstens, which is the innovation of Elia, saw this and said, okay, let me see if I can use your platform to solve a problem that I have right now. So what if instead of people sending measurements data or entities sending measurements data, I have different forecast suppliers And then I create an environment like an everlasting, ever-going competition, okay? So multiple suppliers join our platform at any time, individuals, companies, or whatever, and then they sell the forecasts. I mean, they send forecasts to the platform. Elia, as a purchasing entity, creates a monthly price for this competition, and then according to your performance, you get something out of this market, okay? So if your forecasts are good, you have a low forecasting skill score, for instance, you'll get more than if your forecasts are bad. In the end, what we do in the middle is ensemble forecasting. So we combine the different forecasts and hopefully create something better than the best forecaster, okay? That's one of the goals. So what are ensembles? You probably are aware of it. So this is also a way to help or ease extreme errors. What happens is that forecasting companies do not always fail in the same way. So if you average them out, you can ease extreme errors. And also helping balancing biases. So there might be companies that are leveraging on a specific weather source, and if their model for some reason has a bias in certain scenarios, they will underestimate or overestimate. And if you have someone that underestimates and another one that overestimates, if you do the average, for instance, you get something in the middle, so it helps correcting biases. So how does this work? Now that you know the platform, you know the goals, how does this work? So we organize this in market sessions. And the concept of a market session is to have a gate closure time. So if you are a trader, for instance, that needs to make bids in the market, you need to have the forecast at a certain time. So market session establishes the window in which you can submit forecasts. And the market makers, so in this case, Elia, that wants to purchase forecasts, they basically, what they do within that window is they publish forecasting challenges. And the challenge is basically, they say that I need forecasts for the day ahead, for wind farm X. In this case, they are buying forecasts for the offshore national aggregated capacity of wind in Belgium, or for the solar, for the solar generation in Belgium. So national level aggregated solar and offshore wind. So they open 2 challenges every day. Then forecasters see these challenges, they submit their forecasts within that gate closure time. And then we run the ensemble forecasting. And once measurements data is available, we evaluate the forecasters and distribute the payment that the ones in the top, so in this case Elia, is willing to pay for that session. And that's it. It's very simple. So in terms of modules, what we have is outlier detection. So this is crucial, and we learned that in the hard way. So in the beginning, what happens is that forecast suppliers, even companies that you probably know of, submitted wrong forecasts. So this is probabilistic forecasts. Sometimes they submitted quantile 90 instead of quantile 50, and it was a mess. So outlier detection is crucial here. Then forecasting. So here we had a mix of regression models and statistical approaches, which worked better than the regression models. And then we have the evaluation and payment processing. So we take care of everything. What Elia needs to do is, or the market maker needs to do, is to send measurements and then know how much they need to pay to each other, to each forecaster, supplier, okay? That's it. This is the roadmap that we had with Elia. So we had a few months to iterate on that first version, measurements-based, to this version that you have right now, so the ensemble of forecast suppliers. We started testing this for offshore wind day-ahead forecasting, and then we are running also, in parallel now, forecasting of solar, okay? Again, aggregated national solar or offshore wind. This, you can see here the number of companies that are supplying forecasts in our platform and how that grew over time since the beginning. So we started with 13 companies, now we are around 30. We have around 30 companies submitting forecasts every day to our platform. And the good thing of this is that, for instance, 30 companies were submitting forecasts for wind of Elia, and then they said, okay, we want to also finance forecasts for solar. And those 30 companies just changed a few flags and started doing the same thing for another use case. So for instance, if a new company came in with, let's say, load forecasting or price forecasting, whatever, it's time series forecasting. These 30 companies could migrate to that new company very quickly, okay? And quickly you have instant access to 30 suppliers of forecasts. So in terms of forecasting problems, as you see in red, you have there the outliers and abnormal forecasts. And our outlier detection approach removed this. And then there is the over or underestimation, so normal problems. The good thing there in the top, the figure in the top shows in gray, overlapped all the forecasts from all the suppliers. So you see that they do not predict the same at all. Okay, they are always in constant disagreement. And then in black you see the observed values, and in red you see our ensemble forecast, which, as you can see, the value of ensembles, it is in the middle. And it is better than most of the forecasters. And then the problem with this, and this is, we started with regression models, which quickly stopped working, because what happens is the best forecaster, so here let's say that you have as letters a forecaster supplier, okay, a company, and then you have the ranking in terms of root mean square error, for instance. And what happens is that in January, the best company is not the best in February, and it's not the best in March. They keep changing. The top 5 companies or even top 10 companies keep changing over time. Remember that we have 30 companies in the platform. And the first 10 are very competitive. You can see here just an overview of actual rankings for all the different companies there in the left for the first 3 months of this year. And you see, for instance, the F18, the ensemble is the best in terms of ranking. So it's not always the best every day. You see here, each column is a day, and you can see the ensemble does not rank first every day, but it's more consistent. And consistency is important here. And that's why it is on first place in average. But you also can see that the first place in terms of forecasters, so F18, is not always the best. It starts being very good, and then suddenly decays in performance in February, and suddenly in February the conditions of wind changed, and is not good in that condition. And then it starts being good again in some days of March, and then it keeps changing over time. Regression models cannot tackle this. So what we ended up with was a weighted average. The weights pass through an exponential function to accentuate differences. And we also combine this with outlier detection and some other steps of the pipeline to produce the forecast. So something simple worked way better than something complicated. You can see here also, besides the best forecasting changing between months, the best forecaster for the deterministic forecast evaluated for root mean square error is different from the best forecaster of a probabilistic forecast, which is here evaluated by the mean Winkler intervals. Also, here are the results. And there are some important points here. So if you look in average, and these are results since we launched this, you see that the average root mean square error, for instance, for the top 5 forecasters is this, and our ensemble is better 5% than the top 5 forecasters in average, and they are very competitive. And you never know who are the best top 5. This is in average, okay? Every month it keeps changing. Then over the best forecaster for wind is 3%, and over the current Elia provider, remember that Elia had to select the supplier, and the current supplier, it's better 7%, okay? And almost 9 to 10% on probabilistic forecasts, so quantile 90 and 10. And you see these numbers are if you look at comparing our ensemble with the best forecaster each month, remember it changes. We are not always the best, but again, consistency is key. If you compare the ensemble with the average of the top 5, you see that it is better every month. And we're talking small percentages for wind, for solids very big. Okay? 15%, 10%. This at a national level with 7 gigawatt capacity is a lot. Okay? 7% is a lot in terms of error. And this is these scores are just for the root mean square error on the top. And here you see root mean square error and mean Winkler intervals. So, need to speed up. Just to give you an idea of the size of the companies that rank first are not always the best, or the ones with the more people, okay? Then, if we take out the top 3 forecasters, the results remain the same. The errors remain almost the same throughout the period. We have a dashboard for this, so Elia can check the errors and performance and so on. And then, just quick remarks. So, again, we focus on renewable energy forecasting, but this can be expanded to other use cases. It's time series forecasting. So, if you want to join doing forecasts as an individual or as a company supplying forecasts, contact us. If you want to play a role like Elia to purchase forecasts for your company, collaborative forecasts, also contact us. So we have a proof of concept going until the end of the year, at least. So feel free to contact us, and we can work this out. Just to wrap things up, we at INESC TEC, and in line here with the spirit of LF Energy, we are pushing for open source. We are starting to put things open source, and Predico, the initial version of it, is open source, okay? So if you want to check all the open source software of INESC TEC, you can go to this page. We have a lot of things for energy, from renewable energy communities planning and operation to day-ahead real-time optimization tools to support multi-energy system aggregators. We have a lot of things open source already. And then also to say that for instance, the Twin Rev platform in which INESC TEC developed a module also is soon to be available at LF Energy. And this is, as you can see here, a digital platform for grid optimal planning and operation, which has already some end users using it. You might recognize some as the operators in Greece. And this is an effort from different centers, different providers, from Greece, here from Aachen, from the university, that will also hopefully soon be available in LF Energy. So feel free to see more about it. That's it. So if you want more details about Elia proof of concept, you also have all the details of this in that page. Questions?
Yeah. 2 minutes.
Is it also applicable for DSO?
Yes, if it is time series forecasts, sure. The Elia said once that it could be even Coca-Cola cans. If you want to predict Coca-Cola cans for the next week, yeah, it can do it. What we are focusing right now is on day-ahead forecasting. Soon, intraday forecasting, okay, hopefully until the end of the year. And those are the first 2 use cases. Yeah. Actually, we are talking with other DSOs, with other companies to start now from September to participate on this. So, again, we are opening the system now that it is robust. Also, it's important to mention that it has right now a 99 point something SLA, so the service only crashed during the blackout in Portugal and Spain, because the machine is hosted at INESC TEC. It's a proof of concept, and in that day everything went down. So besides that, that's another thing that is important for the forecast buyers, to ensure that I have a forecast. So yeah, that's it. No more question?
So now changing for the different session. Good afternoon. My name is Fábio Coelho. I'm also a senior researcher from INESC TEC. We are this year a platinum sponsor for LFE. And in this spirit, what we are showcasing in this presentation is what is about to become one of the new recent LFE projects called the LFE Semantic Energy Framework. The result of these open source projects soon to be on LFE is a result of the H2020 Interconnect project. This was the largest H2020 project within the framework. It was a project led by INESC TEC and 49 other partners within Europe. We were funded at the time 36 million by the European Commission to work on interoperability systems, and particularly to work on top semantic interoperability for the scope of energy. Okay, so this is kind of a sneak peek of what our consortium was at the time, and the most important thing is that to the project that will soon become an open source project here in LFE, we did not do this alone on INESC. So we started with the help of all of these colleagues, and the project that we're going to showcase was a project that already went through some serious proof of concept on the field. For more than 2 years, we deployed the system that we're going to see in several different European countries, okay, together. So these 7 different pilots, and also an overarching pilot that also went across some of them to provide interoperability services and interoperability systems for services in energy and non-energy use cases, okay? And it was key for our project that we counted with the support as beneficiaries in the project of some of Europe's widest white good appliances manufacturers, such as the Elia Group, Daikin, Miele, Whirlpool, and also others that were then essential to prove in the fields what we're going to show you today. So in the top, INESC, TNO, and Vislor were kind of the key supporters for the solution that we're going to show you. And also these 3 are the key institutions that we will move forward on this project for within LFE. So what were our results in terms and objectives for interoperability? We started, we started with a background for our project already for some services in a high TRL, okay? Some use cases, and most importantly, the base for our interoperability standard, which is semantics. And particularly in this field, we departed from a set of protocols, SAREF, S2, and FIWARE, that in Europe were already being developed by some partners and allowed to create some dictionaries in terms of essentially providing what are the essence of devices, their characteristics, and without any doubt, clarify what were the differences and the characteristics of these devices. And this is key for semantic interoperability. Going along, we had use cases that were already somehow existing, not using this type of technologies, but they were already starting in the field, such as what became afterwards our flagship use case, the delayed start of smart good appliances, okay? So this is a use case that we will see a little bit ahead, but this was what anchored all of the developments across all of our different manufacturers that we have then tested. The interoperability part was then built on top of SAREF. So this was our core ontology that we used. This is, of course, EU-centric. But something that we want to explore afterwards within LFE is that all of the different technology that we built is actually domain agnostic. Okay, so we built it around use cases for energy. We built it around the central use of SAREF as this key ontology, not only for energy, but which has its energy as a wide anchor. But the technology that we'll see here and the open source community that we're trying to build around here will be usable in different domains. We want to use it in healthcare. We will be able to do that. We will want to use it in auto industry. We will be able to do it. What is the contrary? We need to change our key driving ontology to derive and characterize that domain. So replicability is also at the core of this project. I want to show you a bit in our project where our use cases were. So as I was telling you, we had use cases in 7 different European countries. In the end, we touched 600,000 households across all of these different users, where they became users and demonstrators for the technology that was showcased here in a series of more than 40 different use cases demonstrated in TRLs up to 7. And the common thing that we had here is that all of them used our semantic interoperability framework as means to provide all of the data exchange capabilities, but also reasoning capabilities within those use cases. And that was a strong movement for us and a strong proof of concept that we had so that we could now bring this for LFE and to continue this as an open source project. The key use case that I was telling you about, so the delayed start of white good appliances, is actually a very simple use case. But then in the field, proved to be quite challenging because of the differences that exist currently in how manufacturers deploy their appliances, what is their priorities, and most importantly, what is the way that their systems communicate with the devices and how they plan. So what is this use case about? Very simply, imagine that I'm a user and that I want to have my dishwasher or my dryer just running a cycle, okay? And I want to be able to delay the appliance. So pretty easy use case. I want my laundry to be done by 9 p.m. this evening. So I know that by that time the cycle will be run. But what happens in the meantime? Most usually, the machine will just remove the time that it has for the cycle and it will start at that point. But with the moving array of DSOs, in particular DSOs providing dynamic tariffs within Europe, this is becoming very dynamic, and ultimately the use case will deliver this decision towards an energy management system that in the meantime will decide what is actually the optimal time for this cycle to run. As long as my cycle is completed by 9 p.m., I am happy with it. And so, but what happens in the meantime, and how can we coordinate all of this? What are the prices of energy? What are the priorities of the EMS? What are the other devices that the EMS has to control? How can I communicate with the device? Can I get the status of the device? Is it running? Is it stopped? So all of these is a very difficult scenario and use case technically to then deliver this. And so this was the base for the framework. So if we now think about the use case and considering it in the diversity of different capabilities and protocols, within my household, my single EMS could be operating at least 5 to 10 different types of devices and brands. Ultimately, if every device comes from a different brand, this will become soon a nightmare in terms of mediating all of the different message exchange and all of the different status. And we ultimately need to understand that if one manufacturer has a cycle and has a status for a cycle named A, and a different one has the same exact purpose for the cycle named B, ultimately this will become a nightmare in terms of understanding what each one of the different devices is accomplishing. And so for this, what we did in this project was to consider in the end our framework, what we call knowledge interaction. So this is how we can interact with data. And we are able, through the semantic protocol that we have, in this case, SAREF, to actually accommodate a set of service-specific adapters, as we call them, translators in practice, which allows us to actually reach for different systems, so multiple different EMSs if we want. On this side, multiple different low-end protocols that are able for us to contact to the devices itself. And these ones were protocols that we used and demoed in the project, so SPINE, S2, most importantly, and enable us through our platform to actually accommodate some translation and interoperability among all of these devices, okay? In the set of interoperability levels, okay, and this is for those studying semantics, a common picture to look at, we are currently in this scenario. So when we have a data model where multiple parties just align on a common data schema, the type of messages and what should be included on that, we usually land here on number 3, so synthetic interoperability. We know the objects, we know what they mean, but that is interpretable by a human. The machine itself will have a very hard time interpreting and doing translations at this level of interoperability. So what we wanted with Interconnect was not to replace existing solutions that would already deliver interoperability levels at number 3, but it was rather to create or to be in the field with the extra one, with number 4, which is the semantic interoperability, which is essentially delivering value and meaning on top of an existing syntactic interoperability protocol, okay? And this is the essence of what allowed us to actually provide all these multi-manufacturer data exchange. So as some means for context, what we have here is the example of two digital platforms. One, for instance, uses Web of Things and the other uses eBuzz and Spine. And this is the common case. So we do a handshake, we agree, we go through tons of paper describing what the protocol is about. Then maybe after some months we do have the actual protocol implemented. But then if a new change needs to be put in place, the cycle just go again, okay? And improvements will take a longer time. So what if we could actually include some adapters, and instead of relying on the agreement, on the actual syntactic data exchange and the protocol itself, what if we agree on the domain? So, and this is the key exchange within after interconnect, is that our handshake is now based on what is the meaning of data, and not only on what is the exact protocol in the one specific version and how it was built. So what interconnect provided was a new proposition towards semantics in the way that we start with the syntactic interoperability approach, which is already there in the field, deployed, in some cases more mature, in others less, but it's deployed. And what we do is to look at all of the different APIs and interfaces which are available for one given use case, and essentially we go through one process which will deliver what is a semantic representation for that given API and meaning. When we do this, in the end, we will be ready to achieve semantic interoperability, and what we get is a series of graph patterns that describe us what is the purpose and the meaning, without any doubts, for each one of the different endpoints or methodologies that we want to do. For data exchange, to trigger the appliance, to shut down the appliance, to change the cycle, you name it, as long as we can come up with a new graph pattern to represent that type of a data exchange, we are then ready to actually use the framework that we are going to show you. So the framework itself, at the time of the project called SIF, under LFE it will call Semantic Energy Framework, allow us to have services and digital platforms mediated through an interconnection point, so an adapter, and it will actually allow us through some common features on registration, on providing security, providing links and verifiability, will allow us to actually provide all of this adaptable data exchange between components is starting to build and starting to create an ecosystem. In practical terms, what happens is that our generic adapters, our connectors, will allow all of the data exchange to happen through a broker, a semantic broker called the knowledge engine. And this semantic broker has one property which is a little bit different from others, in the sense that in our framework there is no central pool of data or central location of data where data is moved from, where queries might or not be provided. All of the data remains in the origins of the services, so this is behind our generic adapters, and data is exchanged only at the time when we need actually to trigger one exchange between different services. So what is kept is a reasoning on what each one of the different digital platforms and services can provide, the graph patterns, what actions can or not be actioned for each one of the different services, and then at the time when that exchange is ready to happen, it happens directly between the adapters that will provide for that service. So this is already an increased level of security that we can include here. In practical, what we have is, if I have service A and I have service B on this side, mediated by the framework, I will be able to on the base of a graph pattern, and this is just one example, to use only 4 different knowledge interaction types to actually map all my possible different data exchanges. And these 4 different knowledge interactions, called the ask and the answer, allow me to ask queries and provide for answers directly through them. And the most powerful ones, these post and react, allow me to post information without actually knowing beforehand that an answer will be provided. and will allow me to react with events along the way that data is going to be published. And most importantly, on the basis of my graph pattern, I can have total or partial matches, which will allow me for a high level of flexibility to create systems. So, looking back to what I was saying in the beginning in terms of changing the domain, if I just change the way into which my graph pattern is built, so the domain and the base ontology, I can still use all of my different foreign knowledge interaction types to represent the data exchange in a given domain. Change the domain, change the graph pattern, and we are good to go. And it was on this basis, with only these two pairs of four knowledge interactions, that we were able to create and do all of the exchange in all of these different use cases and systems. In practical terms, at the core of our framework is our knowledge engine. And essentially what it does is that it creates what we call knowledge bases behind each one of these services. You can see it as these little pools or small pools of graph patterns, which are known across the network. So this is all decentralized, okay? There is no single point where all information lies. All of these knowledge bases will, by the dissemination of information, at some point in time, know what the others can or not do. And it's on this basis, on this knowledge, that then graph pattern matching, either in full or partially, is done to allow all of the different answers. So this means that if I'm a service here, and if I'm seeking for information which is partially provided by this, and partially provided by that one, I will get actually an ensemble of answers that is collected on the different answers that all of the different peers in the network will provide for me. And I'll have then the flexibility to decide which one to take based on quality, based on response time, and ultimately based on how fit that data according to the domain representation, that is the ontology, is according to what my initial query was, okay? So this is a powerful component which allows me to set all of these different types of use cases with only these four different knowledge interactions. So ultimately, the use case that we were talking in the beginning, in the end looked like this. So we had the framework in the middle, okay? We had several different energy management systems, which allowed us to swap even in the services. And on this side, we had the appliances, in this case, in this example for Miele and Whirlpool, being being mediated by their own infrastructure at the provider side, being able to do all of these different these exchange to provide for that use case. In this case, Whirlpool used a totally different and proprietary protocol on their side. Miele and BSH were using a common based protocol based on the EN 5631, which is the eBase Spine IoT. And on this side, two different energy management systems that could swap on the EMSs and also on the appliances themselves. So this provides us with a lot of flexibility to change. And currently, 2 years after the project ended, we still have two pilots with roughly 200 participants ongoing, with the system still up and running. Besides Whirlpool, Miele, BSH, and Daikin, also at the time of the project, we are also able to extend and perform the tests with Elia EV chargers, okay, also covering this spectrum of applications. So, to close, soon enough, in the next weeks, this will become a project in LFE. We will start to create the community together with you all. It will be supported by INESC TEC and OSV's Lore as the key and initial supporters. We already have a GitHub site, so even though it currently is still empty, it will be it will have the contents there once we launch the project, and we can hope that some of you, if not all, could join our community at the new project LFE CEF. Okay, thanks. Go ahead.
Thank you very much for the presentation. Very interesting. And one quick question. You into the ontology, and I just wanted to understand the knowledge engine and it doesn't need to run on it's not like an additional sort of server in the middle where it runs that sort of translation.
It is not. It is not. The way it works is that we have we can have in the network this knowledge engine with different instances running. So there's no no single point.
You're about 10 minutes over.
You are right.